Hi. So today I'm presenting my work FedDUAL RDual strategy with adaptive loss and dynamic aggregation for mitigating data heterogeneity in federated learning that has recently accepted in transactions on machine learning research in 2025. So let me introduce the authors. So I am Ashutosh Tripathi. I am former student of Rajiv Gandhi Institute of Petroleum Technology, India, and currently a data scientist at published in Sapient, and Pranav Shahu, Shri Pranav Shah, and Samrat Mondal are from the Indian Institute of Technology, Patna, India, where Pranav Shahu has done PhD from Indian Institute of Technology, Patna, India, currently a data scientist at Walmart, and Shri Pranav Shah and Samrat Mondal are the associate professor at Indian Institute of Technology, Patna, India. So let us start with the presentation. So first see what is federated learning. So as we know, in centralized learning, we share the whole data to the central server, which arises the privacy concerns. So in federated learning, it's a distributed machine learning approach where we have multiple clients that collaboratively train a shared global model. And data always remains local. We do not share the data to any central server. We only share the model updates in the form of gradients or weights. So in this manner, it helps to preserve data privacy and security. Let's see it step by step. So first, a server sends global model to all of their participating clients. Clients train locally on their private data. So after the training, they send the model updates in form of gradient or weights back to the server. And the server aggregate this or updates to improve global model repeatedly. And we repeat this process until convergence or some predefined criteria are met. So this is how conventional federated learning looks like. So, so before coming into the motivation of our proposed method, we need to understand what are the challenges that are involved in federated learning. So there are so many challenges such as system heterogeneity, communication efficiency, differential privacy related issues, and moreover, the main challenge is data heterogeneity. So what it is, we have non-identical distributed data across clients, that is non-ID data or non-independent and identical basically across clients. So because of this data, we see performance degradation of the global model and very slower convergence. So we achieve very sharp minima that indicates model is converging to very less generalizable solution, right? So we ask key question to ourselves: can static aggregation, the way we have discussed in the previous slide, methods effectively address this severe non-ID data distribution which are causing these issues? So the answer is a big no. So we will see why it's a big no. So for this, we have trained two model, basically two federated model. One is on IID dataset and one is on non-IID dataset. And we have plotted their loss landscape. Loss landscape. So what we observe here, for the IID data, we are getting smooth and wide valleys compared to here with the non-IID data where we are getting sharp peaks and narrow valleys. So that indicates in presence of non-IID data, our generalization is poor compared to the IID data. So we conclude here that traditional Fed average achieves suboptimal generalization under non-ID conditions due to convergence to a very sharp, very narrow minima. So let's see more. So to get into the root cause of the problem, we have done the gradient analysis. So we have taken again the IID and non-IID case, and we have plotted the gradient norm for each of the layer of the model. So what we observe, if you observe closely, only the lateral layers are are showing significant gradient amplification in presence of non-ID data here and here. And in initial layer, we do not see much amplification. IRD and non-IRD's gradient norms looks more similar. So this amplification in the final layers, this is leading to the model instability and poor generalization. So we require target adjustments for these layers during server-side aggregation. Let's see more. So this is one part that we have explored, and we also argue that only the server-side aggregation that we are doing for the final layer, that is not sufficient. Should we also done some client-side enhancement during local training? More specifically, we have proposed one adaptive loss function for local training on the client side. So let's see, uh, let's have an overview first what it does, then we will deep dive more. So it enhances local optimization by allowing clients to effectively explore local minima. So it basically helps to prevent overfitting on highly varied local datasets, which is a classical scenario in federated learning. And moreover, simultaneously, it preserves the global knowledge that global model has learned from all of the participating clients. So it ensures that the optimization benefits from all clients are successfully integrated while it didn't overfit on any of the client's dataset. Let's see more over it. So let's conclude our both the proposed modules. So first, client side, we have proposed one adaptive loss function that helps to balance local optimization and global coherence. And for this, we have used KL divergence regularization, and we have proposed one dynamic beta parameter based on the performance gap. We will see its mathematical parts in some time. And server side, we have done the aggregation for final layers, because as we observe in only the final layers, we notice the gradient amplification. So we have used Wasserian Berry center based aggregation and fed average for lower layers. So it helps to adapt to client learning patterns. So after doing client-side adaptation with this adaptive loss function and server-side intelligence with this Wasserian Berry center-based dynamic aggregation, we achieve a robust federated learning algorithm. Let's deep dive more into our solution. So before deep diving, we need to understand few terms. So the first is KL divergence, basically Kullback-Leibler divergence. So it measures how one probability distribution diverges from a second reference distribution. So if P and Q are two probability distribution, so this is the mathematical formula to calculate it. Then what is Wasserian distance? We also call it Earth movers distance. So uh, it measures the optimal cost or transporting mass to transform one probability distribution to another. So if we have two distributions, so we calculate it like this. This is the mathematical formula for Wasserian distance. Then based on that, what is Wasserian Berry center? So if we have k distributions such as this, and we have associated weights with each distribution, so the Wasserian Berry center is the distribution that minimize the weighted sum of these Wasserian distances. So we mathematically calculate Wasserian Berry center using this equation. So we use this Berry center to aggregate the last layer of client models more effectively than simple averaging, improving robustness to non-IID. Right, so we will discuss more detail about both the modules, client-side adaptive loss function and Wasserian Berry center-based server aggregation. So in client-side adaptive loss function, we have introduced this. So where this is the cross entropy loss and beta is the dynamic parameter that we have introduced, and this is the KL divergence between the probability distribution of client model and the global model. So for probability distribution, we taken the weights of the corresponding model and flatten those weights, and then we have taken the softmax to get the final probability distribution. Right. So let's talk about this dynamic parameter beta. So this is defined as the difference of local model accuracy after the local training and the global model accuracy. So this difference taken by sigmoid is beta. So see, if beta is large, that means the local model's accuracy is greater than global model's accuracy. So you will notice this term will be diminished or will tend to zero. We will have this term. So we are having more alignment with global model. We are not much focusing on local training part. So it helps to prevent overfit, and it also helps to maintain knowledge that has been learned from all of the participating clients. And in a vice versa case where beta is less, so this term will be diminished or will tend to zero, and this term will be dominating. So we are more focusing on this local optimization. Right, so we are preserving global knowledge while enabling local exploration based on this performance gap. So this is our adaptive loss function. Right, so let's talk about server-side dynamic aggregation. So for that, we have calculated Wasserian variation. So we have already seen the formula, how it's calculated. So the actual barycenter calculation is like very computational expensive. So for that, for the practical purpose, we have approximated this NOP algorithm to calculate the Wasserian barycenter. Right. So this barycenter we computed iteratively, starting by calculating a scaling factor gamma using this equation followed by equation 16. So we calculate gamma where we calculate the Wasserian distance between the current estimate and with the current estimate and the probability distribution divided by a small factor. We call it epsilon. That's the purpose is only to enhance numerical stability, and then using this formula we calculate the Wasserian barycenter, and we like use these two formulas iteratively to come up with a stable Wasserian barycenter. We have done some ablation study on these parameters or hyperparameters. You can have a look in the paper. So we calculate this scaling factor gamma using this Wasserian distance between the current estimate and the probability distribution of the client weights divide by this epsilon, that is for numerical stability, and again we calculate the new barycenter with help of this gamma and this lambda factor, where lambda is the associated weights to each of the local model weights. So for the convenient purpose, we have taken the same importance, same weights for all of the clients. So in this manner, we calculate this Wasserian barycenter. We will discuss these steps more in our algorithm. Okay, so let's discuss more first about Wasserian barycenter. So the barycenter that we are calling as P bar is iteratively refined by comparing it with each client's gradient distribution Pi that I have shown Pi with epsilon for ensuring numerical stability. So after convergence, the resulting Wasserian barycenter is used to update the global model. Specifically, we subtract the weights for the final layers with this Wasserian barycenter that we obtained. And we have already discussed, we are doing this for only the final layers, because in the final layers only gradient norms are fluctuating. So they are at that place conventional Euclidean averaging fails to account for distributional variability across clients, leading to biased aggregation that will induce an unfair global model. So here the Wasserian barycenter defined over probability distribution mitigates this by minimizing Wasserian distance across client updates as discussed in equation 15 and 16, yielding a geometry aware and more resilient aggregation strategy for heterogeneous data. So this answers the question why we have used Wasserian barycenter. So the first reason is it operates in a space of probability distribution that helps to minimize distributional discrepancies across clients. That helps to adapt their learning patterns. So we call it geometry aware aggregation for heterogeneous learning behaviors. So that's why it's more robust than simple Euclidean averaging. And for efficient computation, we have approximated it using Synop algorithm. Right. So let's discuss the algorithm of each step. So firstly, we have some clients K and we are doing this process for some rounds T, and we have a global model G at the server that we have randomly initialized. And at the end, we will get a trained global model. So to distinguish the final layers from the initial layers, we define a mask E that can have value or 0 or 1. So it will be 1 for the last layers and it will be 0 for the rest of the layers. So where it will be 0, we will be doing the nav, the vanilla aggregation. And where it will be 1, we will be using our Wasserian barycenter based dynamic aggregation. So we have initialized the weights of the global model, and for the T rounds, we will pick a subset of clients and we will initialize two lists to store their weights and gradients. And then for each client in the parallel, we initialize that local model with this global model weights, and we will train that local model using the loss function that we have proposed on their local data set. And then we will append their weights and their gradients in this list. We will do this process in parallel for each of the client. After the local training part has been done on the client side, we come to the server side, and for the server side, we see for which layer the mask is 1. We take the gradients and we compute the Wasserian barycenter as discussed, and we subtract the weights of the final layer by the Wasserian barycenter and where mask is 0, we simply perform the normal vanilla averaging, and hence we update the whole global model. So we repeat this process till T round, and at the end we get the trained global model. So this is our algorithm in detail. Let's talk about some experiments. So for experimental setup, we have used three data sets: CIFAR 10, CIFAR 100, and Fashion MNIST. And we have taken 100 clients in total and 10% sampling per round. We are out of 100, we are sampling only 10 clients per round. And batch size is 32, local size is 3. And to induce severe non-IID conditions, we have taken this alpha parameter at very small 0.01. So this helps us to simulate the real world scenarios. And we have taken two model, LeanNet model for Fashion MNIST and BGG16 model for CIFAR 10 and CIFAR 100. And we have taken these 8 baselines to compare our proposed method with. Right. So firstly, we have achieved top 1 accuracy. So by the table on all of the cases, FedDUAL consistently outperforms all baseline across all data set. And we also noticed FedNova, FedVN, Scaffold. These good methods are even fail to get converged in this severe non-IID scenarios. The next part is we also obtain the learning curve. So we see the learning curve for FedDual is its trajectory is more stable compared to the baselines. And then we also plot how many rounds it takes to achieve the target accuracy for each of the case. So FedDual achieves 40% faster convergence, that is it 40% faster to reach the target accuracy in all of the case. We see here uh, how much how much faster it is in all of the case. So it is more stable and it is also fast. to achieve the convergence. Then we have also conducted ovulation study. So as we discussed, we have two modules that we have proposed. So firstly, we have done experiments using adaptive loss only and doing the vanilla aggregation for all of the layers. Secondly, we are doing cross entropy loss for local training and doing the dynamic aggregation only. Then we are using both. That is our FedDUAL strategy. So we see when we are using adaptive loss only, we notice this performance or for all of the cases is lower than the field average as well. So this helps us to conclude that adaptive loss fosters global and local model alignment, but it lacks the capacity to improve generalization. Hence, we are getting less performance. So we can conclude adaptive loss alone is insufficient to resolve data heterogeneity issue. Right. And then when we have integrated both adaptive loss and dynamic aggregation, we get the highest performance. So it demonstrates that a dual strategy is necessary to effectively maximize model performance. And then next is we have done layer-wise aggregation impact. So we have applied our dynamic aggregation strategy on all parts of neural network. So when we have applied in all of the layers, we see the reduced performance. The performance is the least, and when we apply to the final layers, we get the highest performance. So this also validates that gradient analysis that we have done prior, where we have seen the gradient amplification is only in the later layers, and we also see the performance is highest when we have applied this dynamic aggregation in the later layers only. So, and secondly, we have also plotted the loss landscape for IID, for non-IID scenario only for the Fed average and our FedDUAL. So we see here Fed average achieves suboptimal performance, very narrow and sharp minima. Here we see a flatter surface and wider valley. So it validates our motivation, and it is the proof that we get the better generalization in terms in presence of non-ID data compared to Fed average. And we have also done experiments with different degree of heterogeneity. So we see in this case also FedDUAL achieves the highest accuracy across all heterogeneity levels, and it also shows slowest performance decline when we switch from a higher heterogeneity to lower heterogeneity. It shows slowest performance decline. So it demonstrates superior robustness to varying non-ID conditions, and also uh, also it's like very commendable for real world scenarios. Then we have also done the computational complexity analysis. So for, per communication round. So for the client side, we get this extra big O D. That is for the we are not using the traditional local cluster therapy loss, but we are using our adaptive loss function. So this is same as FedProx, and this is a minimal computation overhead. And for the server side, as we are doing necessary and very center, so we are getting this extra term, IKN square. So let's do amortized analysis. So despite this 35% server overhead per round, we have also noticed this 40% reduction in total wall clock time due to faster convergence of our proposed method. And we are we have given this as per the general assumption, as client side training time is like very greater than the server side training time. Please see in the paper in the appendix section to get more idea about this. And then we have plotted wall clock time to reach target accuracy. So we notice that reach target accuracy proposed method takes like very less time compared to all of the baseline. So it confirms that the theoretical gains in communication round that we have shown in the graphs directly translate to faster real world convergence in terms of wall clock time as well. So we conclude that we have additional computation overhead, but we achieve very faster convergence in terms of rounds as well as in terms of wall clock time. So that negotiate this extra computation cost and make it more useful for real world scenarios. And then we have also done the theoretical convergence for both convex and non-convex setting. So for convex setting, we have achieved the standard. We go of 1 by t, which matches with the rate of any first order method under standard assumption. So this indicates that FedDUAL preserved convergence efficiency while incorporating this Wasserian Bayesian-based aggregation and adaptive loss. And for the non-convex setting as well, we achieve the standard big O of 1 by root t, which is a standard for non-convex optimization. And this, the additional term, this is accounted for Wasserian Bayesian-based aggregation, and its effect is also like bounded. So for the full proof, please look into the appendix of the paper. So let's discuss the limitation. So its primary limitation is the higher computational cost at server, and we have explored the non-IID level SQ scenarios only. So for the future direction, we can develop more efficient Bayesian calculation algorithms, and we can integrate differential privacy techniques here to make it more and more useful for the more sensitive and private scenarios, and we can extend it to further feature heterogeneity and other non-IID types. Thank you so much for listening. Feel free to connect in case of any questions, any feedback, any collaboration, or any suggestion. Thank you so much.